This is section 1.6, inequalities in the book, and I wanted to go over some that you're going to have for your homework, just because I know we'll only get so many done in class, and if you have troubles, at least this might help you with the ones that we don't get to. Okay, if you notice, they're telling us to graph the solution set of this inequality. We call the thing with the less than or greater than an inequality equation. They want us to graph the set over the given domain, and the given domain is real numbers, which if you remember we said we could write this way. It's supposed to be a capital R with two lines. It's kind of squiggly there. So when we solve inequalities, we solve them just like we solve equations. The only thing that's different is if we ever multiply or divide by a negative number, we have to reverse the inequality sign. So I don't think we're going to have to do that here, but let's solve this first and then we'll graph it. I'm trying to get the x by itself still. Oh my goodness, by itself still. Sorry about that. So I'm going to do PEMDAS backwards, and if you may want to write it on your paper, but that means the first things we're going to do is try to add or subtract anything that's added or subtracted from the x to get it to the other side. And we see there's a -5, and so we always say, well, if I'm going to get rid of it, I have to do the opposite. So I'm going to add 5 to both sides. Just like you would on an equal sign, if you do it to one side, you got to do it to the other side. Okay, -5 plus 5 is 0. Remember, I can write it or I cannot write it. And that's less than 9. Okay, we just copy that sign down. So we have 3x is less than 9. We don't usually write the 0. I'm going to put every little thing in because it seems like a lot of you are really struggling. And I want you to understand what's going on, because if you ever catch on, I think you're just going to feel like this is so much easier. Okay, I'm still trying to get the x by itself. It's multiplied by a 3. I've finished adding or subtracting anything I can. If I want to split that 3 off that x, since it's multiplied, the opposite of multiplying is dividing both sides by 3. So I get x is less than 3. Now, what they want me to do, and they want me to graph it, let me go over here and put some numbers on my number line. It's a number line at this point. Okay, we're going to be doing number lines probably in this whole section here. If you remember how to graph these things, where are the x's less than 3? Well, here's 3. It's kind of my boundary point right here, right? I want all the x's less than 3, which would be out this way. Where are the x's less than 3? Well, 2 is less than 3, so you know you're going to go out in the direction of 2. 4 would be bigger than 3. You want the smaller quantity to have the point toward it, and the bigger quantity has the open part. So you want all the x's less than 3. Read it from left to right. We are not going to count 3. If it had a line under it like this, under the inequality, that would have meant we also want to count 3 as a solution, and we would have colored in the dot. Okay, number 3 gives us an example of one where we're going to have to understand that with inequalities, when we divide or multiply by a negative number, we're going to have to reverse the inequality sign, and a lot of times what I say is flip the sign. So if I say that, you'll know that I mean to reverse the direction of it, which means if it's pointing this way, down at the bottom, look at that blue one, I would switch it to point the other way, which is, I think is going to happen here. All right, I'm trying to get x by itself. I'm going to solve this like I do just as if this inequality sign were actually an equal sign there as far as moving things around. It works the same way. And any answer I get, because I'm looking at all real numbers, I'm going to take any answer I get. I'm not going to go, ooh, that one was positive and only want negative like we did the other day, and we threw some answers out. All right, remember, the thing that we always get rid of first is something we could add or subtract. I cannot add or subtract 6 because 6 is not attached. Look between the 6 and the x. They're smushed together. They're joined with multiplication. We would have to get rid of the 6 by dividing it out, and that's not where I want to start. I want to start with just numbers that are hanging out over there that aren't attached to the 6 with to the x with multiplication. And so the 2 is what I'm going to move first. I'm going to subtract 2 because I have a positive 2. The opposite would be a subtract 2. Or I could say add a negative 2 to both sides, but that's the same thing as subtracting. So usually we just say if I have a positive number, I'm going to subtract it. If I have a negative number, I'm going to add the opposite. All right, so we get 0 minus 6x is less than or equal to 6. But 0 minus 6x is just a negative 6x. Just like 0 minus 6 would be a negative 6, except this time it's got an x with it. All right, so now I have this. And remember, I'm trying to get the x by itself. So what am I going to do now? Well, in order to get x by itself, it's attached by multiplication. That 6 and that x are shoved together, aren't they? It doesn't say 6 minus x. It says negative 6x. So I'm going to divide to get rid of it by negative 6. And when I divide, I just divided by a negative. If I divided by a positive, I wouldn't have had to do anything. But because I divided by a negative, I'm going to have to reverse the direction of that inequality sign. Negative 6 over negative 6 is 1 over, I could say negative 6 goes into negative 6 one time, negative 6 goes into negative 6 one time. 1 over 1 is 1, 1x is just x. We just say they cancel out, but that's what we mean by they cancel out. There are mathematical properties going on there of equal fractions and stuff that make that an x. Now x is greater than or equal to 6. So now I'm going to graph this one. I'm going to start at 0, negative 1, negative 2, negative 3. I'm going to skip some numbers just so I can fit things in there. Negative 4, negative 5, negative 6. This would be negative 7, negative 8, negative 9. I'll put a few numbers in there, but remember, I am very limited by this stylus and how this iPad's picking up these numbers. So just try to listen as well as watch. All right, x is bigger than negative 6. So this negative 6 right here is my boundary point. Here it is. They're telling me they want the numbers bigger than negative 6. Well, tell me a number bigger than negative 6. The number, if you're looking for a number bigger than another number, don't you go to the right on the number line? For instance, isn't 0 bigger than negative 6 even? So let me shade toward 0. That's the thing with these inequalities. You don't have just one answer. You have a whole lot of answers, and they're all, anything that is above negative 6 would work. But because they have this little line under the inequality, I also say, oh, they want me to count negative 6 as a solution. So since they want me to count it, I'm going to color it in. Okay? So that's what my answer would look like. Since it's all real numbers, I want all those answers. I'm not going to throw any out. Usually we don't throw any out unless they cause a big problem, like we're trying to take a square root of a negative number, or maybe our denominator ends up being 0 or something. That's the only thing that really we usually throw out. But they're trying to get you to understand domain and range here a little bit better. Okay, now we're getting into a little bit harder type of problem. Do you remember I told you that absolute value represents distance? If I'm standing in one spot and I go north 7 steps, I've gone 7, right? If I go back to my original spot and I go south 7 steps, you know, if we were on a number line, we might call that negative 7, but if I'm talking in real life, I don't say I took negative 7 steps. I say, oh, I took 7 steps from the original spot. That's what absolute values are trying to represent. Mathematicians just wanted a way to show that you're 7 away from something, okay? So we're going to be 7 away from x. So wherever my starting point is, I can go 7 this way, or I could go 7 this way. And they're not going to call going to the left negative when they use an absolute value, because they're only thinking about how far away were you from your starting point. All right. So now when we have something like this, it's not just one thing, because remember, there's 2 different ways I can go 7 away. If I start here, and I want more than 7 away, more than 7, because remember, look at this right here. This isn't saying that I want my distance away from a starting point to be bigger than 7. If 7's like right here, and this were 7 over here, what I'm saying with this absolute value is I want to be bigger than that. I want to go farther away, so maybe I'd be going out that direction. Or maybe I'm starting at some original point, and I'm going 7 away, 7 miles, 7 steps, whatever you want to think about, 7 steps away in the other direction. We end up with something looking like this. Now, on a number line, we would have called that negative 7, that one on the left, wouldn't we? So how do we translate this absolute value, this distance notation, into something we can solve and get answers for? What's going to work in this problem? Well, one thing you do is you copy down the inequality. You say, okay, one of the equations is going to be x bigger than 7. That's going to describe the one on the right. But if you're thinking of this as a number line, and you start at the red dot that I just kind of put little blue dots on, we would want to go to the left of negative 7 to get 7 away from that dot to the left. And when you're going to the left, if you remember, we would use less than to describe that. X is less than what? Well, if this were a number line, we would have called that negative 7, so we have to write it this way. Now, this is going to be one of the hardest things you'll have to ever remember. I still struggle to remember it, and the way that I get it is to draw that number line and think about what they're trying to tell me with the notation, that my distance is bigger than 7 away from my starting point, X, whatever X is, okay? You have to take this one equation here that you started with and break it down into two. And do not do this in your head. I want to see your work, because you're going to get ones you can't do in your head, and you're going to mess it up, and you're going to go, oh, shoot, but it's going to cause you to not do this right. So you've got to practice this. It's not going to just abracadabra pop in your head, okay? Well, on this one, there's nothing to solve. X is bigger than 7. There's nothing to move around. X is by itself, and that's always our goal, to get X by itself. And this is your other answer. That's your answers. If you're supposed to graph them, though, and I believe they did tell you to graph the set, and we're going to ignore the A, B, C thing. We're not even going to do that. We're just going to graph the answer, because this is too confusing to be, I think, doing it this way right now. So what this is saying is one of my boundary points is I'll graph in red, positive 7, and it's let's say it's up here 5, 6, 0, 1, 2, 3, 4, 5, 6, 7. Okay, let's pretend it's right here, because I can't really do that. I want an open dot. I first drew it as a closed dot, and remember, there is no equal sign under that inequality right there, is there? It's just the greater than sign. And I'm going to shade to the right, which is going to be hard to show, but I'm going to put it over here. Remember, we always put an arrow on it. I just ran out of room on my iPad. All right, but there's another answer that I have to graph. I want the x's less than negative 7. So negative 7 is my boundary point. Where are the x's less than negative 7? They're off to the less than, means go to the left. Negative 8 would be less than 7. If you're $8 in the hole owing money to somebody, you're worse off than if you're $7 in the hole, right? That's how I remember this stuff. So on the number line, we would shade to the left. That would be the solution set for that problem. Okay, I'm going to try one more at the risk of running out of room. Actually, I'm not. I know I can't explain that next one on a video, so I'll make a different video for it.